So thank you to the organizers for giving me the opportunity to tell you about this work. So it's work with, well, all my co-authors are in the room, as they noticed. So hopefully I won't say too many false things, otherwise they can correct me. So what this is about non-Archimedean tame geometry. So this morning we saw at length what happens in the Archimedean context. So how do you get a tame geometry in the reals or in an expansion of the reals? Well, one way to do this, and probably the main way to do this this week, is to assume o-minimality. But o-minimality only really makes sense if you have an order. And so if you don't have an order, and in particular if you're in a non-Archimedean setting, well, you don't have o-minimality. But there are various interesting objects that are non-Archimedean and on which you would like, I mean, you very much would like to have something as powerful as o-minimality, because, well, o-minimality does a lot of things, so why deprive non-Archimedeanness of this? So the main examples of non-Archimedean things, well, what I'm talking about is mainly things like QP, so the completion of the rational field with the p-adic valuation, but also, so in general, valued fields. So I will also be talking about a lot about formal power series over characteristic zero fields. And so as we saw this morning, I mean, these objects didn't show up. Well, something a bit like that did show up this morning. These object comes with valuations. So contrary to Matthias, I will write my valuations in the non-historical way. And I will write them as norms, because then what we write on the board makes more sense to Archimedean people and to people that have actually never worked with valuation and are not used to putting everything in reverse, changing every times into pluses, and so for me, evaluation on a field will be a map from the multiplicative part of a field into some ordered abelian group. So for most of this talk, to be fair, the ordered abelian group will be the positive reals. The valuation, you're allowed also higher heights, but it doesn't really matter. It will matter at some point in the talk, but mostly you can assume that, but sorry, I'll write it as a norm, I said. So it's multiplicative, and it has the strong triangular inequality. So as we saw this morning, well, so the triangular inequality this morning was written with a smaller and a min, but it's the same one. Yes, so this is nice. Well, this is both very nice and a curse. So it's nice because the unit ball is a ring. So usually we extend the norms. Sorry, I should norms by putting norm of 0 equals 0, which is just smaller than everything in gamma. And the closed unit ball is a ring. It's actually local with unique maximal ideal. The open unit ball. Okay, and so then you also have a residue field, which in this case is Fp, and in this case is little k. And so now the question one can ask is, what does the geometry of definable sets looks like in a field with evaluation. So, I mean, with no hypothesis at all, this can be very, very messy. So I'm going to ask that K is a little complete. So I'm going to focus on characteristic 0 Henselian fields. Actually, mostly we will focus on equi-characteristic 0, which is meaning that the norm of, the norm of all integers is 1. And so once again, definable sets are meant in the same sense as this morning. So either you choose a language and then you start looking at formulas, or maybe if you prefer, you look at equalities and valuative inequalities, so things of the form P of x smaller than Q of x, where x might be a tuple. And then you close under Boolean combination, products, projections, and all of this. And then you get all the definable sets. And so as we saw, in the o-minimal context, what you ask is that the things in the affine line, so you have a strong finiteness property for subsets of the affine line, and that implies many, many things. So this is o-minimality. So in the Archimedean setting, implies many, many things. So Tobias started listing a few of them. So the monotonicity theorem, the cell decomposition theorem. We haven't gotten into that yet this morning, I think, but then you also have various point counting theorems and many, many things. And yeah, so the question is, in the Archimedean setting, what can we hope for? What finiteness property can we hope for? So first, things look a bit bad. So let's look at C of double bracket T. And let's just look at one of the, so of course you have in definable sets, you have all affine varieties and such. These are fine. So let's take something that actually needs a quantifier, like the most simple things that needs a quantifier. So the set of nth powers, which is the set of x's such that there exists a y, yn equals x. And well, in C of double bracket T, this is a bit ugly. What happens is that this is actually the set of x's such that the norm of x is in nz. So I haven't told you what the norm is, but the norm is the t-adic norm.
This nz is everything.
Oh yeah, sorry. So yes, thank you. Exactly. So the norm here is the norm, the t-adic norm, and so well, this is not a very, I mean, this has a lot of connected components. I mean, of course, we're in a non-Archimedean setting, so everything is totally discontinuous, so it's not clear what I mean by connected components. But there's, I mean, well, what it looks like, maybe I'll try, I don't know how much of a drawing this makes sense, because I'm drawing a non-Archimedean thing onto an Archimedean plane, but whatever. So what we have is a bunch of annuli that go closer and closer to 0. So how on earth is this finite? This is not finite at all, I mean. But still, well, I pretend something is finite, and we'll see what. So in R of t, things get even worse. let's look at the square powers. Well, the square powers, so in R of t, the third powers, they also look exactly like this. It's just being a square is exactly given by the norm. But in R of t now, not everything here is a square. So actually you get something in a little weirder, so you have 0 in the middle, and then you kind of get half annualized. Okay, this, I'm not sure, again, how much this drawing is supposed to make sense, but you only get half of the annualizage all of the time. They're not really lines like this, but I mean, maybe you can imagine them to be lines. But, okay, this is also quite bad. What happened is that there is something very finite going on. And so now, well, okay, maybe let me write here. In fact, what's going on, the finiteness of this whole thing is that it's centered at 0 somehow. I pretend that this is the finiteness going on. So in what way? Well, you can prove the following theorem. So if K is Henselian residue characteristic 0, so what I call the equicharacteristic 0, then if you take X inside of the affine line, definable, there exists a finite set C such that for all balls B, if B intersects C is empty, then B is included in X, or B intersect X is empty. So what this says, so I didn't give I mean, this can be seen from a certain quantifier elimination theorem that I'm not going to talk too much about because it requires objects that I will introduce later. But this is a true theorem that you can deduce, for example, from Basarab's quantifier elimination. But anyway, it's true. And so in the particular cases, in this case and in this case, the finite set is just the singleton 0. Because, well, what happened really is that my annuli were a little bit thicker than what I pretended. And anytime you take a ball that doesn't intersect 0, it lives in one of those annuli. And so either it falls there or it falls in one of the lines. And so either you're entirely in it or you're entirely outside of it. So, so this is what happens. So this, I pretend, is the finiteness we're looking for. Okay, I pretend this is exactly the same as o-minimality. Why? Well, K with an order is o-minimal if and only if for all X inside of A1, definable, there exists C finite such that for all interval inside of K, if the interval with C is empty, then I is included in X, or I intersect X is empty. So this is probably the most complicated way of defining o-minimality that was ever written, but still it is a definition of o-minimality. And point C are exactly the endpoints of the intervals in the decomposition. Oh, the isolated points and the endpoints of the intervals. Okay, so, well, what we've done is just replaced intervals because we had an order by balls because we have a norm. Okay, good. Okay, now we could say, well, okay, we have found our definition of whatever tameness is in the non-Archimedean setting. Well, there's there's a main problem to this, which is that I don't know how to derive essentially anything out of this. So this is not this is not the right notion. Why? So one big problem in the non-Archimedean setting as we said, in the o-minimal setting, the set C, if you take a minimal set C, it's entirely determined by X. So if you take a minimal set that works, it's entirely determined by X because it's going to be the border of X, exactly the border of X. In the non-Archimedean setting, C, minimal C, is not determined by X. So the typical example is in the non-Archimedean setting, if you take a ball, any center of the ball, any point in the ball is the center of the ball. So in fact, so if B inside of K is a ball, then any point of B has the property on the left. So I just realized that I wanted to give this a name so that I stop writing property on the left. So I say that in that case, I say that C prepares X, or well, X is prepared by C. Yeah, so if you have a ball, any point in B it prepares the ball. Actually, any point in the smallest closed ball around B prepares the ball, but so there's no nice. I mean, you can't find a canonical set that prepares your sets in the non-Archimedean setting, and this is going to be a lot of trouble. So in the o-minimal setting, if you start looking at the proofs, if you look at for the decomposition theorem, and you always use the fact that that you're prepared by your border. You use it all the time. So here, well, what we need to do is to, by hand, explain how the set C depends on X. So we're just going to refine the definition to explain explicitly how C depends on X. And so it gets a bit messy. In particular, because there's a very important parameter space that's hidden in what I've done so far that I will need to make explicit. So actually, it already appeared in Matthias's talk this morning, but just as the tilde operation, the tilde relation. But it's usually called the leading term relation. So once again, I have my field, my valued field K with a non-Archimedean norm. Well, really evaluation, and. And so we consider this group. Why not? So take the multiplicative group and quotient it by things that are close to the unit. So by the things that are in the unit ball, open unit ball around 1. So this has many names. It's usually in the modern literature called RV. Why is it called RV? Because you have the following, so actually let me put a cross up there because I don't have 0. You have the following short exact sequence where probably I forgot to write what this is, but this is O mod M. So you have a ring and a maximal ideal, so you have a field, and on this side you have gamma. well, actually, okay, norm of k should be, so that is subjective. This is better. So that's why it's called RV, because it's really an extension of the valuation, the value group by the residue field. So it wraps up the two together. And this is highly relevant to what we've been doing, because so if C is a finite set, a maximal, well, the fibers, well, maximal balls disjoint from C are exactly the fibers of this map where little c is in big C. Probably this is let me call it A so that this is clear. Okay, so if you, well, you can compute it if you want. But so this is exactly what we've been, well, and so in particular, X is prepared by C if and only if X is a union of fibers of RV of this map that I'm going to call RVX minus C. Okay, so in fact, this leading term business was already all over the board at the top, except maybe it wasn't apparent yet. And this thing is going to play a very important role in the theory, because well, one first attempt at improving the theorem would be to explain that if X is defined using certain parameters, then C is also defined using those same parameters. But what we need to do is to be a bit more subtle, because we will need parameters that range not only over the field, but also over RV. And actually worse, but we'll see that later. So an improvement on the theorem up there. So once again, we take K 0, 0 Henselian field. And so now I take a subset of K, and I take X, which is definable over A union RV. So maybe I'll put that into quotation mark for now, and then explain what exactly I mean by that. Then there exists C inside of K, finite, A definable, such that what? Well, so that prepares C. Well, of course it prepares C, but it prepares X, I mean. So I think so far we haven't really cared about where parameters are for definable sets. So let me say a little something about this. So, well, X is A definable. What do I mean by that? I mean that it's defined, so if you think in terms of formula, it's defined by a formula where you allowed all the basic symbols of the language plus names of elements from A. If you want to think in terms of how Matthias presented things this morning, you start with polynomial equalities and valuative inequalities whose coefficients are in the ring generated by A, and then you close under all the other operations. So essentially, X is definable if it only uses polynomials over the ring generated by A. So I've not told you either. So here I was doing something more complicated because not only am I only allowing polynomials over A, but I'm still allowing parameters in RV. So what do I mean by that? So, well, either somehow you add RV to your language and then you figure out what it means, or if you want to stay in a simpler context, A is A union RV definable if there exists Y inside K cross K to the N for some N, such that, and which is A definable, such that the fiber NB, well, or little a, no, maybe, okay, B in K to the N, such that X is exactly the fiber YB over B, and YB only depends on RVB. Okay, so this seems like it has parameters a bit all over the field, but in fact, this parameter only depends on what their RV is. Okay, so that's what an A union RV definable set is. And so the theorem, the theorem up there with control of parameters tells you that if you define over A union RV, you can prepare with a set that's already just A definable. So the RV parameters here don't really play a role. I mean, they allow you to define many more things, but they will not complicate how to prepare. So, so this is almost. So I'm going to put a false definition and then immediately correct it. So this is almost what's called zero h-minimality. So now you may be a little worried because h is not going to move, but 0 is very certainly going to move. So, so what is this? Well, this is exactly if the theorem happens. So so you take K with norm plus more structure is 0 h minimal if for all A inside of K, all X inside of A1, which is A union RV definable. I probably forgot to say, yeah, X was inside A1 again. Then there exists C finite A definable that prepares X. Okay, so this is not the right definition because now we come to small uniformity issues. So I want, well, this definition has a few problems. In particular, if I have a family of definable sets, I want to prepare it rather uniformly, and this does not imply that. So there's two ways to solve this problem. One way is if you're not too afraid of formulas, you're not too afraid of elementary extensions, you can say for X star, for K star, elementary extension of K. So this is just asking that essentially the interpretation of formulas in K star coincide with the interpretation of formulas in K, and I'm not going to say much more about it because I'm going to give another definition that does not use elements on S. And then you just put stars everywhere. So yeah, so the right definition is not only do you look at the structure, you also look at all its elementary extensions. And if you've learned a bit of first order logic, this is because then you get the compactness theorem. And so you can uniformize this statement for free. So, well, of course, I could also just ask the uniform version. Yes?
But, I mean,
Yeah, but this is just a Henselian field.
Oh, you want to be outside of the container?
Yeah, I add plus structure.
Okay. Yeah. Plus structure, but still
No, plus structure. Nothing, anything. So I'm just using the theorem as a definition for something. So of course, yes. So what the theorem says is that Henselian equicharacteristic zero fields are 0 h-minimal. Okay.
And there you also allow positive context?
I allow anything, except I don't know any positive characteristic examples. So.
Want to change the definition, like in the mixed characteristic already.
Yeah, but I'm going to get to that. Yeah, also this doesn't work in mixed characteristic. Hopefully I will have time to get to that, I'm not sure, we'll see. R0H minimum. So when I say Henselian 0,0 field with no further structure. So maybe now is a good time to point out that, in fact, you can prove that, so all that I've done so far, you can also do with Henselian fields with analytic structure, in the sense that I'm not going to make precise. And then they also get to be 0 h-minimal, because this is also true for them. So we know examples of 0 h-minimal things that are not just pure fields, or pure valued fields. Okay, so equivalently, sorry, I was about to write the version where I uniformize everything. Equivalently, for all y inside of, sorry, so let me write it properly. Okay, let me call it W, it's in my notes. For all W inside K cross RVK, A definable, there exists a finite C inside K. So here I'm not changing my model anymore. There exists a finite C in K, which is A definable, such that, so here, when I say a definable set inside K cross RVK, I mean the same as above, which is that it's really inside K cross K to the K, but on this variable, it only depends on the RV of the variable. So it factorizes through this thing, finite such that for all psi in RVK, there exists, no, sorry, the fiber W psi is prepared by C. So the thing you get out of this elementary nonsense is that for free you get that you can prepare uniformly when parameters vary in RV. So if you want, this is well, so these two statements are equivalent, and this one doesn't mention elementary extensions, so maybe you prefer this one. Okay, good. So have we made much progress? Well, some progress. I can prove that if K plus structure. Yep.
Now you've covered those things.
Yes?
You need uniformity in A also, right?
You're right. Sorry. No, I don't. Do I? I do. You're right. You're entirely right. Yes, you're right. So let me take this definable. Well, all finite sets are definable.
But
No. Oh, yeah, sorry. C is going to vary. Sorry. Yes, you're right. For all A in Kn, there exists a C, which is A definable.
no.
Yes?
There is one
No, I think this is right. Finite, search for C, blah, blah, blah. No?
No, now the C is not uniformly defined.
It is.
For every A there is a C, but he wants there is a C that for every A, right?
Yes.
Yeah, but that's false.
No, there's a family, a defined family.
Yes, oh, and you're saying, because I'm not compact, okay, you're right. Oh, damn. Well. Okay, I should have stayed with the elementary one. Yes, so there exists a C inside K cross Kn such that for all A in Kn, Ca is finite. So this is definable and prepares blah, blah, blah.
By the way, this O, is that an O or a 0?
Zero, it's a 0.
Oh, 0.
I don't know if it's better. No, it's worse. But it's a 0. It's a 0 h-minimal.
And definable now in this lower word means 0 definable.
It doesn't matter. Of course, you do, if you know how to do it for definable, you know how to do it for 0 definable by just removing the parameters. Because Imi was right that this was not the right definition. Thanks. But we have made some progress because if we take a field with evaluation plus stuff and we assume that it's 0 h-minimal, then it's Henselian. Okay, we haven't made much progress because I think this is the only thing I know how that follows from 0 h-minimal. Okay, so now we'll be very courageous and I'll give you the actual serious definition, which is LH minimal. So L is a positive integer. And so you say that, so once again, I'm going to write the wrong definition, and then I'm going to pretend that you all know what an elementary extension is. So K plus stuff is LH minimal if for all A inside K, sorry, if I need to define something first. So, almost here. So if lambda is an element of the value group which is smaller than 1, I can define RV lambda to be K cross 1 plus lambda m, where lambda m is the set of all, is the open ball of radius lambda around 0. This is smaller than lambda. Okay, so take A here, and then let me try to copy my notes so that I don't make a mistake again. If for all, yes, so A in K, lambda in norm of K1 cross. Yes, probably I don't want 0. 0 is a bit, is terrible because this is just K cross, but anyway. I mean, it's defined, but it's not very interesting. So for all lambda, small valuation, sorry. This is the problem of changing the direction of things. Sorry, integer or omega, or infinity, slash omega, depending on whether you want to, how you want to write it. If for all A, and for all x inside of K, which is A union RV, well, sorry, and all B inside RV lambda to the L, which is I union B union RV definable. There exists C, which is a definable finite that prepares C, prepares X. Hopefully my co-authors are happy with that definition. No, sorry. They're not happy because it's still wrong. Ah, damn it. Lambda prepares C, meaning that X, what? X is a union of fibers of the map RV lambda X minus A, where A ranges in C. Okay, so in fact, if you have RV lambda parameters, you have certain balls that are just the preimages of RV lambda sets of this point, and these are not prepared. I mean, okay, they are, but in a complicated way. Not by anything definable. So you can't hope for better than lambda preparation, but you ask for lambda preparation. Okay, so once again, this is the wrong definition, because we need to uniformize everything. So what we really need to do is ask that for all k star elementary extension of k, and then put stars. Oh, okay. This is bad notation. And so this is really the RV lambda of k star. And this inside k star, which is definable, blah, 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 blah. Okay. I'm not going to try to write it, but you have an equivalent. I mean, the going to elementary extension, the only reason we do that is that you get a uniform. If you have a family of things parameterized by field points, RV points, and RV lambda points, not too many of them, with L many RV lambda points, then you're prepared in this uniform way. And this is the equivalent definition. So yeah, so maybe now is a point, is a moment to point out something important. In the o-minimal case, you don't need this elementary extension nonsense, because the canonicity of C is very helpful in helping you show that, in fact, if it holds in K, it holds in all elementary extension. I don't expect this to be true for h-minimality. I'd be extremely happy to be proved wrong. But I expect that, I mean, something fishy happens, but who knows? So for now, this is the definition. Good. So I was hoping to be there earlier, but we'll see what I have time to finish. Okay, I have 5 minutes left. So maybe quickly, I can tell you examples. So I mentioned, well, I haven't written the theorem, but in fact, these are all omega h minimal. It means that I can put as many RV lambda parameters as I want. So here I was bounding the number of parameters I could put in RV lambda, and the infinite version is just that I don't care how many parameters I have. So if you add analytic functions, they are also LH minimal, and if you and then for those who know what those are, if you take no-minimal power-bounded theory and you look at the associated T-convex structure, there are one h-minimal, which is one of the reasons why we defined one h-minimal at some point. So maybe I won't have time to give you fun theorems, but I want to point out one thing in the 5 minutes I have left.
So one h-minimal, but not more than one? Or?
We don't know. Maybe. And maybe they're all the same. We don't know that they're all different. There's many things we don't know. So one h-minimal is important. And I am just going to try to explain briefly, well, try to convince you why this is not a completely ad hoc case. Because, well, 0 h-minimal seems reasonable. Omega h-minimal seems reasonable. Why would we care about one parameter? Well, because you can show that there is a geometric reformulation of one h-minimal. So k plus stuff is one h-minimal if and only if. Let me try to not write something wrong again. So for all elementary extension, once again, if you don't like elementary extensions, you can write a uniform statement that will replace it, but it gets more and more annoying. And all A inside K star cross RV, well, union RV of K star. Where am I? There exists and a definable f from K to K. We have two things. So first, there exists C, a definable finite, such that for all B inside of K star ball disjoint from C, there exists mu B in the valuation group such that for all x, y in B, the norm of f of x minus the norm of f of y is equal actually to mu B x minus y. So if you're one h, so it's if and only if you're one h minimal, then one thing that does happen is that you can prepare functions. This is very close to being the monotonicity theorem for o-minimality if you think a little about it. So there is some way to prepare functions so that this happens. And then secondly, the set of x's such that f minus 1 of x is infinite is finite. So this condition is necessary if you want to have any form of good dimension theory, because you want the dimension to decrease, so you don't want infinitely many infinite fibers. So the point is that if you have both, then you're one h minimal. And those two things, unless I made a mistake.
I'm not sure. I always thought that again, your A now is allowed to contain functions from RB. So
Yeah. I think you can, well, okay, if you want, I checked it this afternoon and I think it was okay, but let me make the stronger statement. Yeah, but I mean, the stronger statement is even truer, so.
Now I get it again.
This.
Oh, yes.
Oh, yeah, yes, sorry. Yes, of course. It's just for in my head, it was the sort, okay, and not the field, I agree. But anyway, so maybe I have 3 seconds left. Or, yes, I have exactly 3 seconds left. So, what? Or mu b. Okay. Anyway, yes, so there should be k stars everywhere from the moment it's defined instead of k. But so, yeah, so I think this is a pretty convincing case as to why this is not a completely crazy notion. Because it's equivalent to something we want for finite dimensional, to have a good dimension theory, and some property that's essentially the monotonicity theorem, and that's extremely important. So it's essentially, it's in the non-Archimedean setting, it's often called the Jacobian property. Actually, the Jacobian property is a strengthening of that we also get for free. But, and this Jacobian property is used all over the place in non-Archimedean geometry to define motivic integration, to define, I forgot, many things. I had other examples, I think. But so yes, so now 3 seconds. So this is telling you that if you have basic geometric tame behavior, you actually get one h-min, but if you have one h-min, you get tremendously good tame behavior, because I'm not going to write the theorems because I'm out of time, but you get that if you take any function, actually not only do you have something like a Lipschitz thing going on, but you're actually approximated by your Taylor series, by your Taylor polynomials up to whatever you want, on balls that avoid a certain finite set C that depends on how good your approximation, you want the approximation to be. You get a cell decomposition theorem, you get stratifications, and eventually we also get point counting on curves, and this, I believe, is the topic of Floris's talk on Thursday. So I think I will. Oh, and maybe I should quickly say, but I'm not going to define anything. There is also a version in mixed characteristic of all of this, because one goal, as I said, was to talk about QP, so we haven't talked at all about QP. So it's messy to define, because essentially you need to put integers everywhere in the definitions to account for the fact that the valuation of the integers are not 0. Or another way to see it is you take your mixed characteristic thing, you take a very large elementary extension, you look at the smallest valuation, 0, 0 valuation on it, and you ask that it's one h-minimal, and it's the same.
So this theorem is stochastic 0?
No, this is probably, yes, this probably requires, just to be, I'll say 0, 0 just to be sure. Maybe it does, maybe it implies 0, 0. I'd have to think about it. I think we use it in the proof, so I think it's characteristic 0, 0. But if you, maybe this already tells you that the valuation of integers cannot be big, but I'm not 100% sure, so I'd rather not say something false. Okay, thank you.